All right. So that's solubility of solids and liquids. Now, how about the solubility of gases in liquids? Solubility of gases in liquids. Can a gas be compressed?
Yes.
If you compress a gas above the liquid, what is the gas going to do? If you start pushing on a gas above a liquid, what is it going to do? The gas. It's going to have no choice but to go inside the liquid. So the solubility of gases in liquids increases with increasing pressure. So solubility of gases in liquids increases with increasing pressure. Okay? And now it decreases with increasing temperature. So if you heat water, what happens to the gas in? It goes into the gas phase. But if it was in the gas phase, it doesn't matter. It leaves or it escapes the solvent or escapes the liquid. Okay, so if a lake is very shallow and the sun is heating that lake, will there be oxygen inside that lake?
Not very much.
Not very much, because the oxygen is going to do what? Escape the liquid. So can the fish breathe inside that lake? No. As a result, the fish might die, or the fish are not going to live in that lake. And what happens to the plants if there is no carbon dioxide being released by the fish? And the plants die. So everything dies. Okay? So if the lake is too hot, it's called the thermal pollution. Okay? So this lake here, does it have fish in it?
I think so.
Yes, it does, because that lake is about 10 to 12 feet deep. Okay? So the top is going to be very hot, but the bottom is going to be cold. In the middle of the day, are the fish right on top of it?
No.
Most of the time you can't see it, because they are where there's oxygen. On the top, there isn't a lot of oxygen. So if you go to feed them, let's say at 1 or 2 p.m., they're really holding their breath to eat. Down here on this side, you ever fed the fish? No? On a charter school? Oh, the turtles, oh yeah. Yeah. Alright. There is a law that predicts how much gas is going to dissolve, and that law is called Henry's law. So Henry's law tells you how much gas will dissolve in a liquid. Okay? And it's like this. The solubility of the gas is equal to Henry's law constant. That's why this is called Henry's law. Times the pressure of that gas above the liquid. So this is the solubility. This is Henry's law constant. And this is the pressure of the gas above the liquid. The solubility is given in, what could be a
Moles for.
could be whatever, moles. Pressure is in what?
Yeah.
Pressure is an ATM. The concentration units could be molarity, yes, moles per liter. Could be ppms, could be anything, okay? But if I tell you that this solubility is in molarity or in moles per liter, and I tell you that this pressure is in ATMs, what are the units on Henry's law constant?
moles over liter ATM.
Yeah.
It's a question on the test, okay? Maybe not this one, some other crazy stuff. Okay? You'll have to know that in order for me to get this, I must multiply this by something that has what? ATMs. So ATMs cancel out, yes? Where's ATMs going to be at on this Henry's law constant? It is going to be on the bottom. So here's ATMs, so it can cancel with ATMs. On the top, you're going to have moles, and on the bottom, you're going to have liters. So ATMs cancels with ATMs, and you have moles per liter. My expectation is that you do this all the time. Okay? Now, can I form a solution from two different liquids that they dissolve in each other? Let's say everything I tell you dissolves. Can they form a solution, two liquids? Hello?
Sure or not?
Yes. Can you form a solution with two gases?
I don't think so.
Of course you can. What is the definition of a solution? Homogeneous mixture, yes?
Oh, yeah.
So is this homogeneous, or you can see the oxygen molecules and the nitrogen molecules?
No.
Can you see them?
No.
So I can. So that is a homogeneous mixture. That is a solution made of a gas with another gas. Can you have a solution made of a liquid and a gas? Of course. Can you have a solution in which there is a gas in a liquid? Yes. Can you have two solids together? Yes, you can. They just need to be homogeneous. Okay?
Okay.
Yes or no? Meaning all possible combinations occur, and I have on the slides, whenever you read them, you will see some examples of them. The examples are not going to be on the test. What is on the test is that you have to know that all possible solutions can form possible combinations of solids, liquids, and gases. Can you have a solution of a solid is the solvent and the gas is the solute? Is that possible? Is it? Yes, of course. Should we do some problems?
Yeah.
Do you guys like math? Or you are mathematically disabled? Do you have a mathematical disability? No. You sure? I don't know if I can believe you or not. We'll find out, okay? So calculate the concentration of CO2 in beer. You guys like beer, don't you?
We're technically not allowed to tell you that.
Well, this is science, okay? We are scientists. Everything is experimental.
I like that.
If it was bottled with a partial pressure of 4 atms, obviously of CO2, and I am going to say Guys, who has PLTO with Mitch today? Mitch says that the PLTO session will be right after class at 10 o'clock. You guys knew that?
Yeah.
Okay. All right, guys. So what's this about? This is about the solubility of a gas in a liquid. Of course, you kind of have to know that beer is a liquid, yes? And most people know that beer is a liquid, right?
Most.
What girl doesn't know beer is a liquid? Do you know beer is a liquid? You with a banana. Are you one of the minions? All right. So this is about Henry's law. It is about the solubility of a gas in a liquid. This is Henry's law. And the equation for Henry's law is the solubility. And here I'm going to write the gas. The solubility of CO2 is equal to a constant, which is K, times the pressure of that CO2 above that liquid. This Henry's law constant depends on the water. Okay, it depends on the solid. So all we have to do is, for this very easy problem is, solubility of CO2 is equal to K. There is K. It was given to you. Moles per liter per ATM, and I am going to multiply this by 4.0 ATMs. I feel bad doing a problem so simple on the board. Okay? I do. I feel bad about this. But I still did it. On the test, what can you have? I'm not going to do another one. On the test, what can you have? I can ask you for the solubility like I did here. I can ask you for what pressure do you need if I give you the solubility, yes? So if I were to give you the solubility, you just solve for pressure. In other words, I expect everyone in here to be able to solve for this K or for that P. Yes or no?
Yep.
Don't tell me later, oh, you didn't do a problem. It doesn't matter, I didn't do a problem. Because you told me you were not disabled in math, yes? If you would have been disabled, that would have been a different story. So let's do this. What is the percent, let's say percent glucose?
Okay.
What is the percent glucose
That'll be moles per liter.
if 13.5 grams of glucose dissolved in 100 grams of H2O? And let's say the molecular weight of glucose is 180 grams per mole. A molecular weight of H2O is 18 point, let's just call it 18 grams per mole. So when you are trying to calculate percent by mass or percent glucose, what equation are you going to write down? The ppm equation?
No.
Which equation are you going to write down? Percent mass equation. Percent glucose is equal to the, hello, mass of solute, and the solute in this case is glucose. How do you know the solute is glucose? Well, it is present in the lowest amount. I told you, most of the time this is obtained by finding the number of moles, yes? But you don't have to do the number of moles. You can see 13 is smaller than 100, right? If they were close, then you got to count moles, but this is kind of obvious here. So the mass of glucose divided by the total mass times 10 to the 9th, yes?
No. 100%.
Times 100. How do you know it's 100? Because this here says percent. It would have been 10 to the 9th if I would have asked you for what? ppbs, yes? This is not ppbs, this is percent. So, another very easy problem. the mass of glucose, what's the mass of glucose? 13.5. Divided by the total mass, and the total mass has glucose in it, yes or no? Plus 100 times 100. Now, some of you mathematical wizards in the past have thought that this 100 cancels with this 100. Yes? Does this
No.
100 cancel with this 100?
Not when you're adding.
Please. Okay? So, how much is this?
12%.
11.8%.
How much?
11.8%.
11.9%. Okay, 3 sig figs. Okay? It's supposed to have here maybe something like that. Doesn't matter. 3 significant figures. That is the percent glucose. What's the percent water?
Times by 100.
The percent water is 100 divided by 13.5 plus 100, yes? Or you notice that this solution has how many substances or how many components does it have? It has 2, so they must add up to what number? Into 100. So the percent water is 100 minus this. So percent water is 88.1 because this is a 2-component system or 2-component solution. How's that?
Good.
Everybody getting an A so far, yes? Seems to me like this is an easy class. Right? What do you mean no? That's hard? Because I do this in, what is it, in high school chemistry. Right? That is 1025, my friends. Don't let anybody lie to you. So calculate the concentration in ppms. If 5.4 micrograms. Guys, you watched the video? You did? How many of you watched the video? Raise your hand. Yeah. How many videos have I posted for this class? 2, 3? Now, you don't watch them. I don't do this anymore. You hear me? I check. I know who's watching them and who's not. Just in case you didn't know. If you're not watching them, I don't do it because it's a lot of pain. I gotta go home, I gotta occupy my computer with downloading the video, rendering the video, posting the video, all of these things. And I do it at night. So I work for you at night, so you should work for me too. Now don't feel bad. I will get it back on the test. So, what do we do here? Excuse me? Well, I don't even know what I'm doing. What are we doing first? Yes, we need to convert, we do.
You don't have to because it's such an insignificant.
No, what do you mean insignificant? We are insignificant. Okay, this is not insignificant, okay? Not insignificant. If it were cocaine, believe me, that's not insignificant. All right, so we are looking for what, guys? Tell me. ppms. If we're looking for ppms, we should write what? ppm equation. What's the ppm equation?
Mass of component.
Mass of component. Of course, the mass of the solute, in this case, divided by total mass times 100, right? times 10 to the 6. This is why this is called parts per million. There's a million right there. Okay? So what we need is the mass of the components divided by the total mass. So I need to have both of these numbers with the same unit. Okay? Is this one the same unit as this one?
No.
No. So I gotta convert somebody, okay? Let's convert this one. Okay? Let's convert 5.4 micrograms. There it is. What goes on the bottom here to cancel out? Micrograms. And on the top, the only thing you know how to relate a microgram to, which is a gram. The one goes in front of the prefix, and then you write what the prefix means. If you don't understand what I said, because you never took a class with me, that's okay. You still won't understand it. Micro means what? 10 to the...
No, that's not.
Very good. So you don't know your prefixes, do you? There is centi, there is milli, and then there is micro, and then there is nano, and then pico, femto. So this is 10 to the minus 6. Negative 3 is called milli. Negative 3 is milli. Negative 9 is nano. That only leaves what? Didn't you guys take a nano something class? Shame on you. Shame on you. Alright, so micrograms cancels with micrograms, so that's what we're going to write. Look, we're going to write 5.4 times 10 to the minus 6 grams divided by the total mass. And the total mass is 2.5 grams plus 5.4 times 10 to the minus 6 grams. So what's this number going to be? 2.5 plus 5.4 times 10 to the minus 6. It's still 2.5 to
Yeah.
second decimal place. That's what he meant before when he said it was insignificant. Okay? So that is on the bottom is 2.5 because this is such a small amount. It will not change the mass of the solvent. Okay? But you can't disregard it, okay? So ppms would be equal to what? Times what?
Times 10 to the 6.
Times 10 to the 6. What is that equal to?
2.2 parts per million.
How much?
2.2. Is that good?
Guys, everybody is bringing a calculator and trying these problems, yes? And calculator is not a graphing calculator, is it? Or a phone.
Osmolality. That's,
What happened?
Is that 2.5?
Yes, that's not F, that's if. Now, by the way, do you expect the language to look the same on the test?
no.
Will not look the same, okay? It's gonna look like, it's gonna ask for molality, yes? So you might see the word molo. So what molo is, so you might see this word, and that means molality, yes? And you can kind of comprehend that. And it's gonna have two numbers. What equation do we use here?
The molality equation.
The molality equation. Very nice. If you know that you have to use the molality equation for this here, you already have half of the problem beat. So what goes on the top here? Of what? Solute. Okay, yeah, component, solute, fine. Divided by kilograms of solvent. Is it not liters of solvent? No, liters of solvent is molarity. This is molality. Times 100, yes or no?
No, times moles.
So it's times nothing.
It's nothing.
Times nothing. So I need the moles of the solute. Do I have the mass of the solute? Yes, I have the mass of the solute. All I have to do is convert that mass of that solute into moles. And the molecular weight was given to you because that was nice enough. You divide by the molecular weight as you did in high school chemistry, yes? And what do you get for this?
0.96 moles.
Glucose is C6.
This is what I get. Is that good?
Yes.
Okay. So here's molality. And molality is lowercase italics m. And the moles of the solute, which is 0.241 moles, and I am going to divide this by the kilograms of solvent. I did not have a plan. Now I go, how much solvent do I have? Tell me how much solvent do I have? 25 what? 25 milliliters. This is what I have. Yet what I have to put in there is in kilograms. I have to go from volume to mass. How do you go from volume to mass?
It's in grams.
Using density. Okay, I'm going to multiply this by the density of water. Okay, because I don't have a density of this solution. If I had a density of the solution, I will multiply it by the density of the solution. So since that's the density of water, since I didn't give it to you, you multiply by the density of water. So this is 25. What is this going to be? 25 grams of H2O. Now, will the density of water be the same as the density of this solution? No,
If it's equal.
okay? Because I have added this stuff to it, okay? That may change the density. Now, that still doesn't mean you can't do the problem. If I give you the density, then what do? You write it here. If I don't give it to you, then it is the density of water. Now I need to convert this to kilograms, yes? Grams goes on the bottom, kilograms goes on the top. 1 kilogram is 10 to the third grams. So this is 0.025. Is this okay?
Yep.
So here we go. We write this number here. What does that give us? 964 molality. Okay? This was supposed to be like 25.0. So I'll put there 25.0, there's a 0 here, and a 0 here, and a 0 here, so it ends with 3 sig figs. You want that one on the test too?
Sure, yeah.
You'll have a molality one on the test. Why not? That's 3 points. It's an easy class. From what I have heard, this is an easy class. So you should all get an A. So here we go. Let's do another easy problem. So let's say convert 36% HCl solution to percent. Let's not say. Convert to convert it to mole fraction and convert to mole fraction and molality. And I'll give you a minute for you to try to do or start the problem or think of what you are going to do. I want everybody writing down. What are you gonna do, man? You just got into class, you gotta pee already? Hey. You're like a girl, man, with a small bladder. Go ahead, man, you get up. It's okay. It's not walk in front of the camera, you might have to move the camera. Go ahead. You gotta go, right?
Like a dog, bro. I like a girl. Like a dog.
Like a dog?
Like a dog. Right.
Yeah, you're right. Why are you guys paging through the stuff? It's as if you are looking for something else. I see paging. Are you looking for the answer or an equation somewhere? Okay. All right, you took too long, okay? You failed already. Mole fraction, what's mole fraction? So I want the mole fraction, which is X. Let's say mole fraction of HCl is equal to moles of HCl plus. Now I have a problem writing total moles, okay? I have a problem writing total moles. Because total moles means the moles of solute plus the moles of the solvent, okay? And what is a solvent in this case?
Water.
You have to know that this solution is in water, because if I don't tell you it's in anything else, then you just guess this is a solution in which the solvent is water. Of course, because you are taking this class, you know that HCl dissolves in water, yes? It doesn't dissolve in hexane. It doesn't dissolve in nonpolar stuff, yes? So the two components that you are going to have are HCl and water. So I am going to write here the moles of HCl and the moles of water. It is the total moles, but I don't want you to confuse this. So that's that. I need, in order for me to have moles, I need to have what first? Grams, yes? I need to have mass. And now it's molality. Molality is moles of solute, in this case, HCl, divided by the kilograms of solvent, in this case, H2O. So these are related, right? I need to find the mass first, and then I need to find the moles. I did not give you molecular weight, so this is now time for you to find it. What does this 36% HCl mean?
36 grams and 100.
It means 36 grams, yes? 36 grams of what?
HCl.
Of HCl. And what is the total? Because in order for this to be percent, you have to have a total. The total is 100. 100 grams of what? 100 grams of the whole thing. It's both of them added together. What goes on the bottom of this? Yes. And now this solution has what inside?
Water and
Water and HCl. How much HCl does it have inside? 36 grams. We already established that. Plus, it has to add up to 100. How much is the water?
64.
64 grams of water. Very good. Now you have the mass of HCl and the mass of water. In order to convert from mass to moles, what do we need? Molecular weight, okay, or the molar mass, whatever you want to say. So let's say the MW of HCl is how much?
36 point, I mean, yeah, 36 grams.
36 point what, 45, 35, 55?
36.4.
No, 45, 65, 35, what is it?
45.
CL is 35.
35 point?
36.4.
45?
Yeah.
No, 36.46.
Oh yeah, 36.
You have the height.
36.46? Guys,
Yeah.
what's wrong? Grams per moles. And the molecular weight of H2O?
1 gram.
I'm not gonna give it to you on the test, you need to know how to calculate it. You guys do not carry periodic tables with you? In your pockets? I mean, what type of a student are you? You don't have pocket-sized periodic tables. So, it is how much you said? 18 point?
01.
18.02.
18.02 grams per mole. Okay, very good. All right, well,
So we can take moles of.
now we are going to
HCl.
convert the grams to moles, yes?
Yeah.
36 grams of HCl divided by the molecular weight of HCl, which is 36.46 grams per mole. What does that give you? Let me find my stuff because
0.9.
0.99?
90. Yeah. Yeah.
Well, 2 sig figs from here. 99? This is moles of HCl. And now on moles of water, how much water do I have? 64 grams of water. Divide by the molecular weight. How much does that give you? 3.6 moles of H2O.
Yep.
Yes or no?
Mhm.
Go ahead, don't wait for me to do the problem so you can look at the board. You do it by yourself and then you check. So what are we doing? Mole fraction of HCl. The moles of HCl. How much HCl? 0.99 divided by
The total amount.
the total, which includes 0.99,
And
Plus?
3.6.
3.6. The answer is 0.22. Mole fraction does not have units. Did I say that before?
Yeah.
Mole fraction does not have units. So that's a mole fraction of HCl. What's a mole fraction of water?
So the water would be on the grams is,
Okay. Yeah, you can say 3.6 divided by 0.99 or and 0.6, but you have to know that mole fraction adds up. All the components must add up to what number? To 1, just like to 100. Okay. And if this is
So it's the rest.
0.22 for a 2-component system, then what? What's the other number?
78.
0.78 is the mole fraction of water. We are now in molality. Molality is the moles of HCl. We already have the moles of HCl. Divided by kilograms of solvent. How many kilograms of solvent do I have?
So you put
0.64 kilograms.
I have 64 grams, yes? I need to convert 64 grams to kilograms. So, how much is that? 0.064 kilograms of solvent. 0.064 kilograms of H2O, and this will give you 15 molality. That's more or less. How's that looking so far? I'm not gonna lie to you, I'm gonna put all of those problems on the test. All of them. And then I'm gonna put some you've never seen before, but you could have learned from here. Yes?
Yes.
This is a complaint most of you guys have. Your complaint is that why is it that if your math professor taught you how much 2 plus 2 is, and he taught you how much 4 divided by 2 is, why is it that he overcomplicates this problem on the test and tells you how much is 2 plus 2 divided by 2? Right? Yes or no? That's your complaint. This is your complaint. Well, he taught you that, and he taught you this, you can do that. And if you can't, then you should not get a good grade in the class, right?
All right.
Let's do some more until we get to the fun ones, okay? So far, this is easy points on the test. This one is calculate the molarity. .5 grams of toluene.
Alright.
Where is that?
Dissolved in 225 grams of benzene. The density of the solution is 0.876 grams per milliliter. You need the molecular weight of toluene, yes?
Yes.
Write it down next to toluene. Molecular weight is 92 grams per mole. Molecular weight of benzene, 78 grams per mole.
$78.
Yeah.
You want the molarity, right?
What?
You want the molarity?
Mm-hmm.
That's okay.
So what are we going to do?
Convert to moles.
Convert to moles? That's the first thing you do, convert to moles? So it's like you have a plan. Why do you have a plan?
Okay, write down
volume
the formula
of
for molarity.
Yeah. before-
Don't have a plan, because if you have a plan, guess what happens? Your plan doesn't work out, then what? That's when you start drinking alcohol and abusing different substances, yes, because your plan didn't work out.
My plan worked out pretty fine.
Okay, well, it has worked out so far, but it won't work out forever, I promise you. Okay? All right, so what I'm calculating is molarity. So what I write down is moles of what? Component or solute, and the component or the solute here is, which one is the lowest amount? 5 grams. So this is moles of toluene divided by
Liters of benzene.
liters of, it is solution, it's not benzene.
That's right.
It is liters of solution.
We had 5.
The only one that is solvent is molality, yes? This is not solvent, this is solution. Meaning this is what? Everybody together, yes?
Toluene plus benzene.
So, okay. So first things first, yes? Moles of toluene. I have the mass of toluene, and luckily, I have the molecular weight of toluene. Grams of toluene divided by the molecular weight, which is 92 grams per mole. What's this equal to?
5.4 times 10 to the negative 2 moles.
Okay? That's what I get of toluene. Yes or no? Alright, so what we have to do now is find the liters of solution. Here's where you guys are going to have a problem.
Use density.
I need the solution, yes?
Mhm.
And I have the mass of the solvent, and I have the mass of the solute. The solution has both of these components inside, yes or no? So I have to add them up to get the total mass of the solution. This is the density of
This is
the solution. I need the mass of the solution, and the mass of the solution is both of them added.
Mhm.
The mass of the solution is 5 plus 225 gives you 230 grams of solution. Since I have the density of the solution, 230 grams of this solution. Divided or multiplied? Divided by the density, and the density is 0.876 grams per milliliter. Grams cancels with grams, and what I am going to get is 263 milliliters. You agree? Yes or no?
Yes. And you need to convert to liters.
And now I need to have this in liters so I can write it down there.
Mhm.
So this is 263 milliliters. So this is 0.263 liters. So I go to my molarity equation, and my molarity equation says moles of toluene 0.54 moles of toluene divided by liters of solution, which is 0.263 liters. What does that give you?
207 molar.
0.21 molarity. Don't worry, you will be challenged on the test. Guys, if I teach you the stuff and you learn the stuff, should it be challenging?
No.
It is only challenging, or you only have a problem doing the stuff if what? If I ask you something that you don't know. And the only way you don't know is if I didn't teach you. Yes or no? So, would you call it challenging if I gave you a problem about solving nuclear equations? Would that be challenging for you?
Yeah.
Yeah, that'd be challenging for you because you can't do it. Could this problem ever be a challenge for you? If you learn it, no. Okay, let's talk about something called, talk about colligative properties. I guess I'm not finished writing it. Colligative properties are those that depend on the concentration of solutes. And not on its identity. So does it matter if it is salt or sugar? No, what matters is how much has the salt. I want to tell you that this concentration is in the number of particles. So this is in number of particles. There's a name for this, and that's the Van Hoff factor, which we're going to have later, okay? I don't want to drill you with that just yet. So this depends on the concentration and not on the identity. It doesn't matter what it is, all it matters is the concentration. And if you're in the lab, I explained this in the lab already. You have a container, and this container has a fluid in it. And this fluid has molecules that once in a while acquire enough speed through the collisions in order for these molecules to escape into the gas phase. Yes or no? Yes. Some of these molecules acquire enough energy that they will go into the gas phase. The amount of these molecules that go into the gas phase depend on the pressure and the temperature. Yes? So, but let's say this is at the same pressure and same temperature. This is a number, and this number is called vapor pressure. Because it is the pressure created by a vapor, which has left this liquid. Now, if I add a non-volatile solute, what is non-volatile?
Doesn't react
No. Volatile and reacting have nothing to do with each other.
It's not that. Doesn't affect it.
Volatile means goes into the gas phase. So this solute is non-volatile. What that means is does not go into the gas phase. Okay? Have you ever smelled salt before?
Smell what?
Salt.
Yes.
You have smelled salt.
negative.
You have smelled salt.
They have meat in like salt mines and stuff.
Salt
You
mine.
get the salt and you go,
Oh no.
yummy.
Why would you do that?
You have never smelled salt
Not
because
like
salt
that.
is non-volatile. Salt will never go into the gas phase. You put salt in the stove, and does it melt? No, it doesn't melt. It has a very high melting point and an even higher boiling point. So you've never smelled salt. So what you think smells like salt is not salt you're smelling. something else. Maybe fish urine is when you're smelling and you think it's salt. Okay?
What about the smell of the salt mine?
That's sulfur. That's like,
I've never been to a salt mine, but what I know is that it is not the smell of salt. And like I said, it's the smell of maybe fish urine, or I don't know what else it could be. You know, maybe people's urine, I don't know. Okay? But if it's non-volatile, how about sugar? You ever smell sugar? You have? Yeah. When you smell the sugar, it smells. How'd the sugar smell?
Caramelly.
Sweet, right? And if you put sugar in the stove, what happens to the sugar? As far as I know, it gets brown, yes? It decomposes before it goes into the gas phase. Okay? You just never smelled sugar either. What you have smelled from sugars are called esters. Okay? And esters is the ones that give the fruits is fruity smell. Like mango.
Mm-hmm.
You ever smell mango?
Oh, hell yeah.
How does a mango smell like?
Great.
Don't tell me sweet. A mango it smells like
Mango.
mango. And that smell is an ester. And if it were sugar you were smelling, it would be the same smell. But it's not. So you add a non-volatile solute. And what did this non-volatile solute do to this? Well, this solute dissolved. And if it dissolved in the water, it must be because it likes the water. Yes or no?
Yep.
It likes the water. Okay? Now, if it likes the water, this vapor pressure was created with the amount of molecules that were escaping into the gas phase. And now you add something that likes the water. And what is going to happen is it's kind of holding down the molecules so less of them go into the gas phase. Okay? So what does that result in? A lowering in the vapor pressure. Okay? Because these molecules, do they go into the gas phase? They don't go into the gas phase. So if they're holding down these molecules that want to go into the gas phase, they're not going. This is like your boyfriend holding you down. Yes, that's what I said in the lab. Your boyfriend holding you down. You will not be able to go anywhere. All right. So this produces a lowering of what?
Vapor pressure.
Vapor pressure. This lowering of vapor pressure is called Raoult's law. Okay? That has a name, and the name is Raoult's law. But don't worry about it, okay? I'm going to give you some of that later. Guys, you got to tell me the time at which we're supposed to finish.
9:36.
I'm so excited in this class, I can't realize.
Half an hour left.
Half an hour left?
Yes. Roughly.
Damn, this class is taking forever. Just kidding, okay? Let's do a phase diagram for this business. This is a phase diagram for water, because this thing is sloping to the left. This is 1 ATM. This point here is called the normal melting point. Very good. I would say you guys are, this is normal. And they call this normal, and of course, if that's normal, the rest must be abnormal, yes?
Yeah.
I mean, or some type of issue with this. So if this is the normal one, this one here is not called normal, okay? That's not the normal one. Normal one only at 1 ATM. Very good. This is, what phase is this? Solid. And what phase is this?
Liquid.
And what phase is this?
Yes.
Gas on fire. All right. And this is what?
Triple point.
Triple point of?
Water.
The solvent.
The phases.
Solvent, yes? And the solvent happens to be water, yes? Yeah.
Can you tell us in our lab to remind you about
You have to
Oh,
say
that a solid
something.
has to be free of non-impurities.
What happened?
In order to make a solid, it has to be free of non-impurities.
Yeah, that's what I'm gonna say next. Thank you for reminding me. I said that in the lab?
Yeah.
Really?
Yeah.
I don't recall that event. That's okay, it's good to forget things that easily. So, here's what it is. I did not explain this here before, but I'm gonna explain it now. In order for a solid to form, you need, or for ice to form, you need this hexagonal arrangement of the water molecules, yes or no? I did say this before. My friend here provoked me. So, it has to have the exact distance between hydrogen bonds. This structure, this arrangement, is more open, or it covers more space than if the water was a liquid by itself. Yes or no? Water were liquid like this, they'll be closer together. So this requires more space, lower density. Yes or no?
Okay.
Hello? Okay, good. You understood that from before, at least I said it before. And now, in order for this to happen, let's say I had a potassium here. Would that form a crystal of ice? No, because it has,
Low
let's say, it has something in it that is stopping it from forming the hexagonal arrangement. So in order for the ice to form, what does it have to do? It has to kind of kick that thing out so a water could be there. Okay? So in order for the solid to form, most of the time, all impurities will be excluded.
What are exceptions?
What?
Which, like, what are the exceptions?
No exceptions. The example is the ice in the glaciers. Okay, you ever been to one of those places where the ice is floating? No? Okay. That ice came from the water that is salty in the ocean, yes or no? Or was it a river before? Hello? It was salt water. It was salt water. It came from the ocean. Now that ice, is it salty ice or is it water with no salt in it? Water with no salt in it. And the reason for that is if the ice or if the solid forms slow enough, it will exclude all solutes. Okay? And the ice will always be pure. You ever seen a place where they make ice? Did you know that there are places that make ice? Like blocks of ice?
My fridge.
Your fridge? No. Your fridge is not good at making ice. Fridge is not good at making ice. If you put a glass of water in the refrigerator and you put salt in it and you freeze it overnight, the next day when you look at it, does it look frozen? You've never tried that before? What are nerds doing if it's not freezing stuff? I froze this stuff when I was in high school. What's wrong with you people? If you freeze it, and go ahead, you try it, okay? You put salt, freeze it, it will freeze. But when you look at it, it'll look like it has bubbles in it. And it's not bubbles that it has. What it has is ice that formed, and in the middle it will have water. And that water has salt inside. So there's no salt, and then salt in the one that has, that looks like a bubble. Anyway, that happens because you froze it too fast. Okay? Now the places where they make the block of ice, of course they have clean water too. They don't want to struggle with it. But they freeze it slowly. Okay? Anyway. The solid will always be what?
Pure.
Pure. And if you have a non-volatile solute, yes, non-volatile solute, will this non-volatile solute, meaning the solute that does not go into the gas phase, will it be carried with the water as it goes from the liquid to the gas or from the solid to the gas? Will it be carried? No, because it's non-volatile. So this curve here is going to be the same whether it's the solvent or the solution. So the triple point will decrease along this line. The triple point decreased along that line. Because the solid is always pure, and because the gas is always pure from what? What type of impurities? Non-volatile impurities, yes? So now you go up, and this trend stays the same. Now what happened to the, by the way, in the phase diagram here, this is pressure, yes? And what's this down here? Temperature. And there was a decrease in the what? In the vapor pressure, yes? You can see it. And we can call this lowering of vapor pressure. There are equations for this, okay? So this now here is a triple point of what?
Of the solution.
Of the solution, yeah. And this here used to be, whatever number this was here, and this used to be the normal melting point. And what has happened to the melting point as I added a non-volatile solute to this solution? It was lower, yes?
Yep.
And this is called, because you had a solution and you form a solid, should that be called melting or should that be called freezing? From liquid to solid, what's that called? It's called freezing, okay? I mean, the point is the point, right? The melting point, whether you are, the freezing point and the melting point are the same, yes? The same point, but a different process, yes? Melting means from solid to liquid. Freezing means from liquid to solid, yes? So there was a decrease in the melting point, but this is called freezing point depression. Freezing point depression. What happened to the freezing point? It decreased. So if you have ice and water, right? Lots of ice and lots of water, actually not that much water, and you stick your hand in it, the ice water is supposed to be at what temperature? According to the book. Hello? 0 degrees, yes? At 0. But if you add salt to this, and you stir it and all the salt dissolved, and you stick your hand in it, is it going to be at 0 degrees? No. It will be lower. So if you wanted to cool down beer, yes? And I'm not saying you want to cool down beer, but if you did, this is the way you would do it. You would get a cooler, half of it with ice, and then you add half of it water. So the water and the ice are at the same level. And then you add salt until there is salt on the bottom of this. And you stir for half an hour. And this water will be around from -5 to -10 degrees Celsius. Yeah, really. This will be very, very cold. You stick your hand in it and you won't be able to have it in there for long, I promise you. Okay? So, and the water will stay like that for a very long time too. So now you go and impress your drunk friends. Alright, so here it goes. What happened to the boiling point? The boiling point went up. This was the solvent, and now this is the solution. So this is called boiling point elevation. Very good. You must be taking class in some other campus, right? You know this, boiling point elevation? Who said boiling point elevation? Don't be afraid. From me?
You said it aloud.
Don't be saying this to people, okay? I don't like to hear that. So, boiling point elevation. There is another one called osmotic pressure. And the osmotic pressure, I'm going to give you the equation, okay? Pi is not on that graph. Pi is equal to MRT. And this pi is osmotic pressure. This M here is what? Capital M. What? Molarity. Molality is lower italics M. This R here is the what? Gas constant. And this T you never guess.
Temperature.
Temperature. Very good.
This is really similar to
Which
the
gas
gas.
constant do you use?
The gas constant that cancels out with that stuff.
And that's a
You
pi?
want to use the joules gas constant? So, this here, mathematical wizards in this class, okay? What is the relationship between pi and concentration? Because at a given temperature, the number doesn't change, right? Let's say 25 degrees. There's a gas constant doesn't change. That's changing with this. What are they? How are they related to each other? Directly proportional. What that means is, as the concentration increases, what happens to the osmotic pressure?
Also
Increases. Okay? They are directly proportional. You'll have to know this without me explaining it to you. I explained it for this one. I'm not going to continue explaining it for all. So, if I double the concentration, what happens to the osmotic pressure? It's supposed to double, yes? Very good. And of course, this osmotic pressure comes from this equation. PV is equal to nRT. You remember that? For the ideal gas law. But when you have a solution, we can just leave P, N divided by V. What's N divided by V?
Molarity.
Molarity, yes? That is molarity, but for a solution, it can't be P, because P is for a gas, right? But you can change that to pi, which is still P. Yes or no? All right, molarity RT. Whatever, this is for a solution. That's the ideal gas equation. Okay, there are equations for this. Let's do the equations. The freezing point depression is equal to delta TF. This an F, okay? Look here. This an F. There's no better way of me writing an F. I'm incapable. It's equal to KF times M. And that KF is called MOLO, right? Freezing point depression constant. Okay? It is a constant only for what?
freezing point pressure.
For the freezing point depression. I already said it, I'm not going to repeat it.
Model freezing point pressure.
Delta TB. Delta T means what?
Change in temperature.
Change in temperature for freezing. It's a what? It's a lowering, yes? And this is the change in temperature for boiling. So this is called boiling point elevation. And look at the equation. This M here is what?
Molality.
Molality, yes? Not
Yeah.
molarity, molality. Kf is a constant. There is osmotic pressure. And this here is the pressure of the gas times the mole fraction of the gas times the vapor pressure of the pure gas. Somewhat of a weird equation. So this is the pressure of a gas when it's a solution. This is the mole fraction.
Is that partial pressure?
Yes, the vapor pressure. Yeah. Vapor pressure of the solution. Partial pressure is the same thing. This is partial pressure. So it is. This is the pressure of the gas when it is a solvent by itself, and this is the pressure when it's a solution. This is the mole fraction of the solvent. Okay?
Does that equal
Yeah. Okay, we'll do problems on that so you can understand this. Okay, so this is the vapor pressure. And this is the vapor pressure of the solution. This is the vapor pressure of
Solvent.
the solvent. So this is pure. This is when you add something to it. Okay? Those are the 4 examples of colligative properties. Write them down. 4 examples are lowering of vapor pressure, freezing point depression, boiling point elevation, and osmotic pressure increase. Hmm? Colligative properties. Osmotic pressure increase. The osmotic pressure is an increase. So 2 of them are increases and 2 of them are decreases.
What were these examples of? What were the examples?
You want to talk about the Van Hoff factor, or you want to leave it for next class? How much time do we have left?
About 5 minutes.
5 minutes? So let's talk about Van Hoff factor then.
Go ahead. Please go ahead.
The Van Hoff factor is related to the number of molecules or number of particles dissolved, okay? Not the number of molecules, number of particles dissolved. Van Hoff factor is letter I. Like the imaginary number from math class, yes?
Mhm.
Purpose here is that you know which one is a Van Hoff factor and for what. Okay? The Van Hoff factor of sodium chloride is how many particles does that become when dissolved in water. So when you dissolve this in water, this an ionic compound, it breaks into or ionizes into what?
Na plus, Cl minus.
Into Na plus and Cl minus. How many particles is that? 2 particles. So from one of these, right, you get 2 particles. So the Van Hoff factor for sodium chloride is 2.
Okay.
So what is the Van Hoff factor for what is the Van Hoff factor for that? 4. This will break into 3 potassiums and 1 nitride, yes? So we can say this is 4. What's the Van Hoff factor for methanol or CH3OH? The Van Hoff factor for that? 6?
The OH doesn't break.
Oh.
You mean to say that, what type of compound is this? Is this ionic?
No.
It's not ionic, it's molecular, it's covalent. This stuff does not break. So, Van Hoff factor of 1. What's the Van Hoff factor of sugar?
1.
Does sugar break into pieces? No, it does not. So it is 1. What's the Van Hoff factor of HCl? 2. So, the Van Hoff factor of ionic compounds is equal to the ions that forms. Van Hoff factor of molecular compounds, if they're not acids, is 1. But if they are acids, it will be, for this one, it's a strong acid, it will be 2. But how about this one?
Also, if it's weak and it doesn't dissociate, it stays together.
Yeah, that's right. If it is a weak acid, then we have a huge problem, yes?
That's two.
If it's a weak acid, it's not 2 because all of it doesn't do it. So it is a number that is greater than 1, yes? But this number is also less than 2. It's not completely dissociated, and it's not together. If you go to pharmacy school or if you go to medical school, you are going to calculate this Van Hoff factor, okay? For things that dissolve in your blood, you need to calculate how much of it you have in the ionized form. So there are equations to calculate this. So hopefully you don't have to learn all of this again, okay? I am not going to teach you those equations, that's none of my business. I'm going to introduce the topic only, okay? Okay guys, good luck in your future. What day is today?
Thursday.
You study, okay? We have a test soon. Oh, if you guys want the number of Sonny. Sonny, what's your number?